but this is really cool that the technology is working as well as it is. Ted, why don't you go to the next slide, please? Okay. As the title suggests, I'll be talking about the PC165DNR camera. I bought one, or my wife bought me one as a birthday gift about a year ago, and at last year's annual meeting I was looking for more information about the camera, and Tony suggested that I simply do the analysis myself and come up. And basically, I've found that the camera's documentation is woefully inadequate. There's not much information about the specifics of the specs and exactly how the features work, so I've been writing a missing manual for this camera, and I hope to share what I've learned with you so far today, and I will be putting some files about the camera in the Iota Occultations webpage. Basically, today I'll be talking about some of the features, the specifications, and how the controls work on the camera. I used Gerhard Dangl's Messier 67 still pictures off his website to do a sensitivity analysis. And then I did some video footage of my own measurements of M67, though I'm still in the process of analyzing that, so I don't really have a whole lot to say about that today. One of the main questions about this camera is what's the camera's time response, especially with the digital noise reduction features of the camera. And I'll talk a bit about that. And many people, including Derek, are interested in how does the camera's digital noise response respond to a target that's moving. Derek's interested in things like satellites. So I did a little bit of a drift study on that, and I've got some still pictures showing the results. It's not moving nearly as fast as Derek's satellites, but it gives you a glimpse. And then at the bottom of the talk, I'll talk a little bit about what I discovered when I put a hand control paddle on the camera and the potential to use the camera in a remote setting. Next slide, please. So one of the nice things about the DNR is that it has frame integration. It'll sum up to 256 fields, so 128 frames of video, and it's still sending out the video at 30 frames per second. So as I mentioned later on in the talk, you have your video time inserter is still digitizing the frames at the right time. It's not as though it freezes for 30 frames and then, or 32 frames and then gives you another one. I'll talk a bit about, well, the other cool feature about the camera is it has digital noise reduction, and this is one of the things that we occultationists need to understand as best we can, because it has a strong effect on how the camera actually responds. It's filtering both in time between frames, and it's averaging across pixels in space. The camera has an on-screen display, OSD is the three-letter acronym for that. This lets you change the settings of the camera's exposure and just about everything else using buttons on the side of the camera and menus on the screen. And navigating these is interesting, but it makes a certain amount of sense. The camera's buttons are arranged in a row of 5 horizontally across the side of the camera. This is fine if you're looking at the camera during the daytime and you can see the labels. If you're working at night like we astronomers do, it's a little bit tricky, and that's why I made a hand paddle for it. One term that gets bandied about a lot is the term sense up, and that's basically this integration, frame integration process, but you can have the camera increase the integration time automatically, and for what we do in astronomy, we want to turn that off. Next slide, please. Okay, there were supposed to be several more columns of text here. There were in the PowerPoint that I sent, but unfortunately, okay, I didn't want to go to, okay, that's okay. Basically, I was going to talk about some of the features. This was a list of all the specifications that came with the camera. You can look at it later in the PowerPoint. But basically, I'm going to be talking about the items that are in bold, which are the on-screen display issues, the shutter speed, the gain control, and the digital noise reduction. Next slide, please. Oops, we skipped one, I think. Can you go back one, Ted? Oh, okay. Well, go forward then. Okay, so one of the things I did was to get an understanding of what the camera's actual sensitivity was. I went to Gerhard Dangl's website and took his still pictures that he collected from video of Messier 67 in Cancer and combined it with the table of known star magnitudes in the Sky and Telescope article from 1989. And as you can see in the star chart there are a series of stars that were labeled with letters, and then a table of known magnitudes for the stars in visual magnitude, and blue minus visual. And then I methodically went through and looked at all of Gerhard's pictures and picked out what the faintest star was that I could see on the still picture. This had limitations in that it's a single still frame, and usually when we're looking at videos, we have the advantage of looking at several frames. Next slide, please. So this first set of 9 pictures is still pretty dark. It'll become a little bit clearer later. Gerhard looked at the northwest quadrant of M67 using a 254 millimeter Newtonian. He didn't put any filters or focal reducers in the optical path. He had a nice dark sky. He said it was very cold as well, like, let's see, -5 degrees centigrade, I think he said. And he basically left most of the other fancy settings on the camera turned off, so no digital noise reduction or anything like that. What you'll see in the next 3 slides is an array of his still pictures. The rows are with the automatic gain control set to low, medium, and high, and then the exposure time set to successively longer integration times. So starting at 30 frames per second with 17 millisecond frame times, 2 times that, 4 times that. If you look at the top left picture, basically you can see the very brightest star up in the top left corner and a couple of more that aren't really visible in the PowerPoint, but if you look at the PowerPoint file on your own screen later, you'll see a few other stars, but mainly just that very bright star in the top left corner. And if you look at the lower right corner, at AGC high and 4x integration, you can see a small smattering of stars. So what I was doing is going through each of these frames and looking for the faintest star that I could see, picking the number off the table, and then entering that into an Excel spreadsheet. Next slide, please. So, same set of or same array of pictures with successively longer integration times. And now you're starting to see quite a few stars, especially in the lower right-hand corner. And it's not very evident in these pictures, but you're also starting to see some background noise. Next slide, please. Okay, now you can see, especially at high AGC and at the longest integration time in the lower right-hand corner, you're starting to see that bright star in the top left is really starting to bloom across the whole scene, and you can see a whole bunch of stars. One problem with comparing the picture from the Sky and Telescope article to Gerhard's pictures was that the Sky and Telescope chart really only shows the top left of each of these frames. So one nice thing would be to go back to a larger map of limiting, a not larger table of stars, and try to pick off some more. That little quadruple of stars in the lower right, for instance, there's another set of stars that somebody's measured that I'd like to go back and look at again. But these were enough stars to basically tell the main story. Next slide. Oh dear. My chart isn't showing up here. Okay, this is going to be tricky. I had an Excel. Embedded graphics don't work. Well, they worked in the PowerPoint that I mailed. They weren't embedded as, they were embedded as pictures, but not embedded as office objects. Darn it. Okay. Well, unfortunately, people are simply going to have to look at the PowerPoint presentation later, downloaded from the website. What we have here is a graph of the, let me see. That's interesting, my page numbers aren't even showing up. Okay. Here I've got actually two graphs showing the limiting magnitude as a function of exposure time for all three AGC settings. And the short version of the story is that at 30 frames per second and high AGC, the camera can see a star of a magnitude of a little bit above 12. The little red circle is highlighting the PC164EX2 camera for comparison. Gerhard had taken a series of pictures of those. Okay. Well, we'll see what Brad or Terry can set up here. I'll just keep talking. Overall, the camera gets successively higher faint stars as you increase the exposure time, of course. And by the time you get to 256 times exposure, the camera can see between 16th and 17th magnitude. Okay. And overall, the camera responds as a one-to-one plot would you'd expect if you just increase the exposure time. You know, if it behaves basically linearly. Next slide, please. Okay, we're seeing even less here. Here, what I've done is I've taken the the 3 automatic gain control settings and sort of normalize them to what you'd see at 30 frames per second to see if there's really any departure from a straight line. And so is Steve going to try to display it another way? Let's see. Okay, I'll keep talking. Sorry, you'll have some homework to do, everybody, but I was really hoping this would work out. I had run across this problem before in graduate school, but that was a different situation as far as what the problems were with the graphics. Haha, look at that. Sweet. Please go back one slide. Yes. Okay. Why don't I just hop to this one then? Thanks, Steve. Okay. Here, what I did is I took Gerhard's images. You see one of those in the top right-hand corner, and the red rectangle is a star-free zone in each picture, and I looked at the noise, the background noise in that region, by taking the pictures and pulling them into Photoshop and doing a histogram analysis of that red rectangle as a function of different exposure times, integration times. And sorry about the headings on the table there. It looked good on my screen when I mailed it. It's something, the font size got increased, I guess. Basically, what I wanted to get at was the background noise to figure out what the signal-to-noise ratio was for my limiting for my stars. And the histogram there on the left-hand side is showing you the noise in that rectangle. And interestingly, it's basically a Gaussian distribution. Now, from what I've read about CCD noise, they should follow a slightly different distribution, but this was good enough for what we needed to do here. Next. Okay, let's see what the next slide looks like, Steve. Rats. Okay. Okay, what we're seeing here is that the tables and some pictures are coming through. If they're JPEGs, they come through. If they're from Excel, they don't come through. I thought by pasting them as pictures. Oh, lovely. That's it. Okay, so this is back a few slides. What you're seeing here is a plot of the limiting magnitude as I picked off individual stars versus exposure time. And in the upper left graph, you've got exposure time as multiples of frames, and in the lower right, you have exactly the same data presented as exposure time in milliseconds. And what we have is the 165DNR camera data, and then the one little X that's highlighted by the red circle is the PC164EX2 for comparison. So as you see here, at 30 frames per second with basically all the same settings between the two cameras, the 164 is a little bit more sensitive than the high AGC setting on the 165DNR. But if you go to any exposure longer than about 2x, the 165DNR tends to do better. The little vertical error bars on the red trace are the rough uncertainty I had when I'm comparing stars in the table. I don't have intercomparison stars that have a narrower range of magnitudes to choose from. So for all of these graphs, basically what you're seeing is the uncertainty of the cameras, well, of the stars I have to choose from. Overall, the camera's response is what you'd expect if you increase the exposure 2 times for each successive multiplication, but you see some variation. For a while, the green high AGC setting sort of takes the lead as it should, but at the high end it sort of gets, it sort of falls down into the noise a little bit. So for very long integrations and with DNR turned off, at long integrations it's a little ambiguous whether to use high or medium AGC settings for this camera. Next slide, please. Okay, this is the one I was talking about a little bit later. What I've done is I've taken the data and taken out the trend and normalized it for 1x, or 30 frames per second. And what you see here is that the high AGC setting does very well at 1 frame per second, or 30 frames per second, but then it sort of loses a bit. And basically my data have about a half a magnitude of uncertainty here, so don't take a whole lot away from small variations between the 3 AGC settings. However, overall it looks as though at the higher exposure times, the high AGC setting drops a magnitude or so, and I think this is primarily due simply to background noise. It's a little bit ambiguous, and it would be nice to test this a bit more with more video, but this is an analysis of Gerhard's images, and I didn't have the benefit of video to work with. I'm still working on that. Next slide, please. Okay, I've already talked about this slide a bit. Fortunately, that graph in the lower right came back. In theory, the noise we get in a CCD image should follow what they call a Poisson noise distribution, where it's like a Gaussian, but it's sort of tilted to the left. In Gerhard's stills, I got distributions that look like what you see on the black and white images on the left-hand side. When I looked at some of my own stills from my own video, they looked a bit more like they were Poisson distributed, and I'm not sure exactly why. But basically, I was trying to get a sense of what the noise floor was in the background of the individual stars so I could do a signal-to-noise calculation. Next slide, please. Okay, this is better. So, this is a very busy slide, but I'll walk you through it. On the top left, you see basically the previous graph of limiting magnitude versus exposure time. And then I took the noise data that I'd collected and the brightness of the limiting magnitude stars and calculated noise from a couple of different perspectives. Again, I apologize for the size of the labels on the graphs, but in the top right, you've got the vertical axis is labeled noise mean. So this is the mean digital counts of the background, that background rectangle for the 3 AGC settings. And again, the 164 camera is there as the little black and white X on the left-hand side of each graph. And as you would expect, the high AGC setting in green is the noisiest, followed by the medium AGC and low AGC. I'll skip over that graph in the lower left, but in the lower right, I then plotted the stars' digital counts minus the background's mean digital counts divided by the standard deviation of the background digital counts. And as you'd expect, the signal-to-noise ratio of the low AGC setting is the highest, and the high AGC setting is the lowest. And as you go to longer and longer exposure time, the noise in the background simply increases for all three settings. So the high AGC setting has the lowest signal-to-noise ratio overall throughout. It was always fairly noisy. Next slide, please. Okay, so this summarizes what I did with Gerhard's still pictures. The camera sensitivity more or less follows what you'd expect. When you increase the exposure time 2 times, the sensitivity increases 2 times. However, within the limitations of the table of magnitudes I had, it looks as though the AGC high setting loses a magnitude or so due to noise at the high end. Getting a critical battery thing here. I'm not sure whose that is. A mouse or something. Okay, next slide, please. Okay, several people have wondered about the PC165DNR's time response when you have it set to a longer exposure. When the video actually comes out of the camera, what are you seeing? And he did a very nice analysis of the time response of the camera, and I will simply refer people to his table on his website. The URL for his website is there. Basically, the camera holds on to the video and then exports it, and it's still updating the video as though it were an analog video. So when you timestamp the data with your Kiwi or Iota VTR, you are getting timestamps of the time as they come out of the camera. And then you refer to Gerhard's table and you insert that time correction when you make your reporting of your times. So next slide, please. So the other question is, how does the digital noise response of the camera respond spatially? It's reducing the noise by doing a spatial filter around each pixel by looking at neighboring pixels and doing an average. I've had a hard time getting an actual detailed information about this, so I simply went out and took some pictures myself. I took a video of a group of stars that were near the equator, and I had the telescope's drive running to take the still pictures. So the cameras were the pictures were more or less, the stars were more or less still. And then I turned off the drive to get the stars moving across the scene at sidereal rates. These aren't as fast as Derek's pictures of satellites, but we'll work on that some other time. He's had problems where the PC164 EX2 camera its pixels look weird when you see a satellite moving across the scene. So what I was using was an 8-inch f10 Schmidt-Cassegrain with a 3.3 focal reducer on it, my PC164 camera. The sky was clear, but it wasn't quite as clear as what Gerhard was using. There were probably some variations from time to time due to some thin cirrus moving through the scene. And with my camera and focal length, I think what you're seeing is about 1/4 of a pixel per video frame at 30 frames per second. So the smearing you see in the moving pictures at the bottom at 32x, 32x is 16 video frames per second, or yeah, frames per second. No, you're dividing by 16. And you can definitely see a little bit of horizontal smearing of the image of the star in the moving column. And then with the noise, I took a thumbnail picture of the noise near the star I was looking at there, and then increased it. I stretched it in Photoshop by a factor of 8 so that you could see it in grayscale. So you can compare sets of pictures that have the yellow arrow on them, roughly. 30 frames per second and 4x that's a little bit of a stretch, but the difference there is that you're seeing the natural averaging process of doing a 4x integration. The kind of speckly noise you see at 30 frames per second, and the noise sort of smears out at 4x. At 8x, I have the same settings of the DNR, but I've turned AGC to high, and you definitely see much brighter pixels there in the noise. You'd expect that partly from the exposure time increase, but also the AGC is definitely noisier there. At 16x, between DNR on and off, with the DNR off, you see some sort of vertical striping noise that's more averaged out when the DNR is on. And similarly, at 32x, you're seeing much peakier noise pixels with the DNR off versus on for the same AGC settings. Next slide, please. Okay, this is stepping away from the noise analysis to my hardware alteration. I found it very frustrating to try to use the horizontal row of buttons on the side of the camera in the dark, and I suspected that that the 5 buttons on the side of the camera were simply making a connection between either high voltage inside the camera or a ground connection inside the camera, and that by bringing the button connections out with a cable, I could set up an external button that was oriented north, south, east, west. And as it turns out, it works this way. And I've written up the design for this in a separate document that I put on the Iota Occultations Yahoo website, and you're welcome to look at that, and I'd be happy to answer anybody's questions about this. Basically, you can buy a little switch from some of the mail-order electronic companies that has, it rocks north, south, east, and west, and has a center push to enter button as well. And I was able to make a little hand paddle where I can navigate through the on-screen display menus using this little hand paddle, and it makes it much more intuitive to work with. Some of the cameras already have the buttons arranged in this north, south, east, west arrangement, And unfortunately, with the 165DNR, they aren't. It's a way of reducing the manufacturing cost, but it certainly makes it harder to use as a user interface. One of the fun things was that after I discovered this, I looked around on the web and I found a guy named Kevin Polvek had made the same discovery independently, and he took it much, much further. He brought the connections out with a cable, and he hooked it up with an Arduino microcontroller controlling 5 transistors, pulling these button connections from whatever pull-up voltage they were down to ground. And he was able to get the Arduino to control the camera's on-screen display settings with the Arduino. This opens things up to, if you can talk to an Arduino over the internet, you can control the camera over the internet. He set up a website, or a web page, sorry, where the Arduino drives the website and it drives the camera. He's got a camera up on the top of an antenna mast, looking up at the sky for meteor showers mostly, and he doesn't want to be climbing up the tower to make changes in the camera settings. So instead, he can be in the comfort of his study and controlling the camera up on the radio tower. But it doesn't have to be in your own backyard. You could have a robotic telescope set up 20 kilometers north of your home observatory, and you could have a remotely controlled telescope and a remotely controlled camera, and set up multiple observatories to look at asteroids, for instance. Not everyone has a place they can put a separate telescope, but in 5 years or so, when we have lots and lots of occultations to consider, this might be kind of an exciting possibility. Next slide, please. So, you can read all this. I'll just skim through it quickly. The camera overall can go after some very faint light sources, up to maybe magnitude 17 with a 25 centimeter scope, a little bit less with a conventional 8-inch telescope. At low exposure times, the PC164 is a little bit more sensitive than the 165DNR. But of course, after you integrate a couple of fields or frames, you can start to see fainter stars than this 164 can. As Tony would recommend, whenever possible, use the fastest exposure time you can. And you can play around with setting the AGC to high, but I've found that I usually set it to medium because at high there's just a lot of extra noise in the background. And at longer exposures, hot pixels start to be a problem. If you're doing a drift scan across the screen, you could run across a hot pixel and have trouble. If you can, if you're driving your scope, you can move it around and avoid hot pixels, and that's not a problem. I think used carefully, the digital noise reduction may be useful. As everyone's recommended in the past, it's best to understand your equipment, and there's still it's still a bit of a black box, but it looks as though it softens the stars a bit, but it doesn't do too much violence to the image itself. And again, use Gerhard's tables for adjusting the integration time delay when you're reporting your results. Next slide, please. Okay. Most of these are a repeat of what Tony recommended last year in his Iota presentation. Choose the shortest exposure time you can, of course, and use the explicit exposure controls on the camera, 2x, 4x, 16x, whatever, rather than the sense-up settings that the camera has on a separate menu. Sense-up works automatically where it will simply increase the exposure time as much as it can to get what it decides is a good scene. But if you have the scene is changing in brightness, like if you're doing a lunar occultation, this could be a problem. I couldn't find anything in any of the documentation about the gamma setting on the camera. I think it's fixed at 0.45. So when you're doing a gamma correction in iMovie, you'd multiply it by 1 over 0.45 and get 2.2. Some other on-screen display menu-driven cameras do have a gamma control, but as far as I can tell, the 165 does not. The 165 can be set to color, but for our astronomy purposes, you want to set it to black and white. And there's still some work to be done, but it looks as though these OSD cameras, if you solder things into the switches, you can use them in remote control settings. And these might be useful in the future when we have way too many observation possibilities to work with. I'd love to set up a little observatory at a friend's house, say 10 kilometers north of me, and have a home observatory and then a little robotic observatory as well. You know, buy an inexpensive go-to telescope that you can control with software and then set something up. It would be a lot of fun. I think the next 2 slides are simply references that you can look at later, but want to go to the next slide? Yes. So I looked at a whole bunch of information in the process of learning about this camera, and I thought it would be nice to let people benefit from it by having the references and resources to look at in the future. So that basically concludes my talk. I'm not sure how I'm going to hear anybody if you have questions there in Maryland. I can turn off my microphone, but then I'll have to turn it back on. Chad says, type the questions. Okay. But let me turn off my mic for the moment, and then let's see what we get as far as Terry said you can leave it on, but I haven't been able to hear myself speak through this whole presentation, so I'm not sure. Okay, no questions yet. I didn't give you my email address, but if you have any questions later, people are talking on the chat line here. If you have any questions later, you can email them to me, and I'd be glad to discuss what I've learned from this camera. Okay, I'm going to turn my mic off for the moment and see what happens.